Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So the first session will be on trends in computing, and our keynote speech will be from Dennis Gannon from Microsoft Research on cloud computing and scientific data analytics challenges. Thank you.
Okay, can you hear me all right? Does this thing work? Okay. So actually I changed the title after the one I gave it, is going to talk about cloud computing and the long tail of science. And the theme of this relates to some extent, or I hope to a large extent, to the discussion that we just had in the last hour. So, hey, this works, okay. So I'm going to talk about very quickly what are the challenge of long tail science, what is long tail science in our view. But what I really want to get at in this talk is this question: is there a sustainable financial model for scientific data? And that, I think, relates very closely to the discussion we had. And I'll talk about our data centers and that are powering commercial clouds. We've got a lot of them. And I'll talk about what we've been doing with the Azure cloud in research. Data architectures, and the role of MapReduce. I deleted those slides because I thought this was an hour talk, and I said it's a half hour, so we'll skip that. And mostly you probably know that anyway. And talk a little bit about managing analytics from your desktop and building communities, which brings me back to the main question. So I think you may have heard of this notion of the fourth paradigm and the revolution of science, so I don't have to spend too much time on this discussion. But as you may have noticed, that data is explosion. It's transforming science, not just astronomy, but every science out there. Everybody now is a data scientist. This is something that has happened very quickly, and it has had a profound impact on many disciplines. And one of the things that all disciplines have told us that they need is the technology for publishing data and sharing data in the cloud, to be able to do analytics, especially on a much more massive scale than they have in the past. Another somewhat pejorative name for the scientists in what we call the long tail are the spreadsheet scientists. Right? Spreadsheets are the predominant analytical tool used across disciplines in science. I think astronomy community is well beyond that, but I'm sure some of you still do some spreadsheet work now and again. And so they need to move beyond that. They've got a desktop machine or a laptop, and it's got so much storage and so much computing capability, and it no longer fits with what they need to do. And there's some number of other issues that have come up that have changed the landscape for how they have to deal with science. So I'll talk about the sustainable economic model. So what I mean by the long tail? So I put in sort of the graph here is the size of data collections. And high energy physics is clearly up there. And I put astronomy there too, but I've had astronomers argue with me that they are still they do not consider themselves yet in the same data league as high energy physics. Well, you folks could tell me whether that's right or wrong. Genomics is now, as we've seen, really working itself there. But what I think about is that collective long tail of science that consists of economic data, social science data, behavioral science data, political science data, a variety of disciplines that you see around your universities that you never in the past have seen really very much of in the computing center. And one of the things that's changed things is, as you know, the National Science Foundation now basically requires all the data that goes into publications to be made public. And the universities are currently struggling with this right now. This data has to be preserved. The data must be shareable and searchable and analyzable. Now, you talk to some scientists and you ask them, well, how is your data going? Well, first of all, this is largely from the NSS point of view, an unfunded mandate. This idea
of the mandate, I'm sorry. can't get away with saying that. We do not require all data to be made public. And we can debate that at length, but we do not require all data to be made public.
All right. So it's not required to be made public, although people still have to come up with a data management plan. And that the fact is that people in the UK, I believe the data is now, much of the data is now required to be made public. I just was in Brussels last week talking to folks there, and so it is happening. At some point, we have to deal with it. And it is an unfunded mandate to deal with it. At this, well, I talked to the researchers that I talked to, and it's not...
Yes, but then no.
Well, okay, perhaps they don't understand.
Debate topic.
All right, well, we can debate it, but how many people out here among the astronomy community feel that the data they have there's a pressure to make more of it public from the government? Does anybody sense that?
Well, certainly
Pressure is not a requirement.
well, but
There is pressure.
Well, the geosciences, it's
There are certain specific requirements in specific fields. There is not an NSF-wide mandate.
But most people who get funding.
Yeah, I'm sorry, guys, but I was involved in writing this policy, and it irritates me that you keep misunderstanding it.
Well, okay, so you don't, there may be good reason to make data public that is not a mandate. We'll leave it at that.
If you want more funding as well.
I'm sorry?
If you want more funding in the future, making your data public is certainly in your interest.
That's right. And there's also good scientific reasons for doing that, as we discussed before. But then this is issue of sustainability. You know, how can we create an economic model for this long tail of science? First of all, the government will not directly support an exponentially growing data collection. I've talked to some scientists, and I say, well, how, you want to make your data available for everybody for a long period of time. How are you going to do that? Who's going to pay for it? And they'll say, well, my data is a national treasure. It'll be kept forever. And the government will support it. Well, that's sort of like declaring yourself to be a national park. And that just doesn't quite work. So what we'd like to do, and this is a hypothesis we have, that we've worked on, that we can create, it's possible to create, an ecosystem that supports a Microsoft, how about that? A marketplace of research tools and domain expertise. Okay? The idea is that we will allow, build critical mass data collections in the cloud, and this relates to the discussion we just had, that there's a lot of scientific tasks that others can do better. That was the point that was made earlier, this notion of making research public, which I thought was really intriguing. But there are certain tasks in a research activity that perhaps there's someone out there who is much better at doing that. And that person or that group can provide the expert services to the community to do that. So if we had data collections that were stored someplace that had to be paid for, that we then in addition have expert services available that would simplify the research life of the people that need those services. For example, I remember talking to someone doing computational fluid dynamics around certain solid bodies, and one of the biggest challenges in doing that is building a really high quality mesh of that body. And that is a real important skill to be able to do that. Well, there are people that are extremely good at it, and there are people that have even set up services that will do that for other folks. And actually NSF funded that to get that going. So the idea is that we could, if you provide something that is of high enough quality that people will be willing to pay a small subscription fee. You'd get the basic data for free if you wanted it, because it's there, and it's a community collection. But if you want to be able to access services at a higher level, something that is truly useful, that accelerates your research, because why not let a professional do it, or let a group that is particularly good at that carry out that part of your research for you, then they can also, that would give you a mechanism, since it's almost contractual or through some arrangement, they would agree to cite you in their publications. That issue came up earlier. And so I believe that this is a way that we could build a subscription-based service for a lot of scientific data analysis. So I think Michigan's Inter-University Consortium for Political and Social Research, the ICPSR, is a very good model. They've been doing this for 10 years, providing the social science data community with highly curated, very well-developed data collections, and as well as analysis services. And they've been doing that for at least a decade, I'm not sure how long. And that is completely supported by subscriptions. Most universities, big universities, I believe, subscribe to this for any of their researchers to use. So this is a really interesting model. Why can't we do that? Anybody familiar with that service that they do? If you go on their, if you go on their website, you'll be impressed by the amount of stuff that they offer. And for the researchers, since the university is subscribing, it feels like it's free. So our hypothesis is that we can do this. And as a community, we can do this. And so we're going to try to test that hypothesis. So now I'm going to get away from that for a minute and just talk about the data centers and our cloud platform. We've been building data centers for a while at Microsoft. Microsoft and Google and Amazon have really a massive collection of really very large data centers. These data centers are spread. We've got 2 in Europe. We've got 2 big ones for our Windows Azure cloud platform, 2 in Europe, 2 in the US, 2 in Asia, and more to come. And then in addition to the Azure, we've got a bunch of other data centers. And these things range, our small data centers are maybe 100,000 servers to 1 million in the big ones. So these are really big facilities. Oops, there's one more. And now here's one that is, to give you an idea where the technology is going, this one, let me back up here, in the upper right corner we call a 4th generation data center. And the interesting thing about this is this data center, and this is an artist's sketch obviously, there is no building to it. Okay, we've gotten so good at building these data centers and putting them in large, big, nasty buildings, the size of mini football fields, that we've realized that, well, you know, actually the way we build the containers for the servers, we don't need the building anymore. We simply pull these massive containers up, plug them into a backbone of power and networking, and now you've got a data center. Give you another idea. This is based on these data centers. They cost, you know, $500 million to build, but they're based now on these model of shipping containers. Each shipping container can, or something the size of a shipping container. We haven't gotten away from shipping containers, but they're the size of a shipping container, 40 feet long, and they have as many as 2,500 servers each in one container. So it's completely packaged. It's got the network in it. It's got power outlet. There's basically 3 plugs on one of these things. There is a power plug, a network plug, and maybe a cooling plug, which you pump water in. Now the water in the newest ones is literally the size of a garden hose. It's not a big, fancy, powerful water system, because these things here, like this guy, this is the latest generation. Primarily it is cooled with ambient air. And that's why it can be left outdoors, even in places where it gets extremely hot. If it gets really hot, we turn on the garden hose a little bit. It helps cool it down. So these things are driving down the cost of energy consumption and the simplicity of setting up the data center. You don't even go into this thing very often. If servers fail, you don't take it down to repair it. You wait until a whole bunch of them fail, and then you can either go take it offline and go in and try to repair it, or you just ship in a new container full of servers. Send that one back to the factory. So this is the technology that's used right now to build the large data centers. Now, the properties then of these data centers, they're really providing, you know, information services to many users simultaneously. The deployment of services is automatically managed on virtual machines. Most of you, how many are familiar with, most scientists are familiar with Amazon, I'm sure. Amazon computes, yeah, okay, so people know about deploying things with virtual machines. And it's the same thing in the Windows case, except we have a higher level of services, but now we also have something that's identical to Amazon's. These things provide automatic fault recovery for failed resources. The data replication is already built into this. When you store on our cloud, if you store a gigabyte of data in the server, that gigabyte is replicated at least 3 times, and maybe as many as 7 times. And it could be geographically replicated or even across international borders, but that's your choice. Yeah?
So replication is for?
Reliability.
Okay, so that implies backup? Or?
That basically what this is, the backup. Your data is replicated so that if the server fails, there's at least 2 more copies of that data, and that a 3rd copy will be automatically brought up based on the other 2.
There was an instance of Amazon losing data.
Well, I'm talking about Microsoft.
Okay.
Yeah, actually, that was an interesting case, because in that case, when Amazon lost services, and it was really the customer had failed to select geo-replication because their whole data center went out. And so the customers that had geo-replicated their data weren't even offline. Their services kept running. The customers that were in trouble were the ones that said, "Oh, yeah, it's in the data center; it'll never go down." Power is lost to whole regions. A tornado wipes out something. And
of course, the question is how much more expensive is geo-replication?
For the user, it's no cost. The replication is just a choice. Some people don't like especially across international borders. That gets to be a sensitive issue. And also, those of you that understand about parallel computing, this is designed to support 2 levels of parallelism in this architecture. One level is a given service, say Netflix or something, with thousands of concurrent users. And then within that, you have, or a better example is Bing or what's that other one, Google. It is something that is, you have a lot of concurrency going on in the construction of a search, the reply to a search, lots of parallelism there, and then parallelism across the user base, many concurrent users. And so it's really, multiply those together and you see these things are designed to support truly massive parallelism. Now, though it is not the same as a supercomputer, this is an important point, that the scale of the data centers are really quite large, but the thing that's different about the data center and most supercomputers lies in the network. Those of you who are familiar with supercomputers, and this is an old slide because it still mentions the old Blue Waters design with 40,000 8-core servers, or Roadrunner 13,000 cell processors, and our Chicago data center is 100,000 8-core servers. At the time I made this slide, it's bigger now. So they're very big, but the network architecture is different. In a supercomputer, you spend an enormous amount of money on the interconnection network between the processors. So your computation, if you're doing parallel computing, you have really good, what's called bisection bandwidth. The data that travels between processors can move at very high speeds and with very high bandwidth. In a standard data center, the network is completely different. It's designed to be outward focused so that thousands of concurrent users are coming in and going out, and they're coming in over the internet. And so the network inside the data center is like an internet. It is based on internet protocols, standard IP protocols. And that means you have, if those of you are familiar with internet protocols, they're very complicated, multi-level routing and exchanges. It is not the same as you would see at a supercomputer, which is a very lean communication protocol stack. Now, this is also changing. Amazon was the first to recognize, some people want to do some supercomputing-like tasks inside the data center. So they put up a really nice sort of a cluster, supercomputing cluster within the data center. And Microsoft has just announced that we're going to do the same thing. And so there'll be such a cluster in Europe, another one in the US, and another one in China. And so that'll give people who really need massively parallel supercomputer style stuff, things using MPI, that type of communication with low latency, Yeah, we'll have that available. And of course, you'll pay more for it because it costs more. Now, so what have been my experience working with scientists in the cloud so far? And what I've been doing for the last 2.5 years is running a program which we worked with the various funding agencies, the NSF, the European Commission, National Institute of Informatics in Japan, the agencies in Asia and China and Taiwan, about making our cloud available to researchers so that the researchers could try experiments on using the cloud. And it's been interesting. So far I've got about 90 projects scattered around the world that are up and running on the cloud. Of those 90, about, I would guess, a third of those, so about 30, have really done something very, very interesting with it. To give you some ideas of the types of things people have been doing. Like, for example, we did a big project with the University of Washington on protein folding, where they had a tool that was based on a technology like SETI at Home, which they allowed people to use, volunteer computing to do protein folding. And they had a specific problem in that it has a pretty long wait time to get anything done. And so we had someone from the Baker Lab who set up such a system come to us with a specific challenge that they were working on, having to do with something involving, I believe it was a salmonella, salmonella virus inject DNA. It was a really important protein fold problem having to do with the study of salmonella. And so we got them 2,000 concurrent cores, put their system up on it. So our cloud became the volunteer, and they were able to handle that computation and get a couple of Nature publications, or Nature and a Science publication out of that in about a week or so. So that was quite successful. We've got another project in France with INRIA there, where they're using 1,000 cores to compare fMRI scans of brains together with the associated genetic information from the patient to try to understand how the brain anomalies might be exhibited within the genomic information as particular types of mutations or faults in the genome that would be associated with these brain anomalies. And that project is still going on. Fire risk in Greece, another one from Europe. We had Greece a couple of years ago had some really horrible fires, and they built a service on Azure to be able to take data from around the country to stream it in, to do the analysis and the prediction and the modeling of where the fires might break out. And this then became, because it's on the cloud, it became a web service that could be used from a laptop or an iPad or something that could be in the field. People could, the first responders could actually be querying this and looking where the fire hazards are and what the situation is.
Does this include SQL Azure as well?
Pardon?
Does this include?
Yes, some of these things are SQL Azure related. In these 3 cases here did not use SQL Azure. But SQL Azure, for those of you who don't know, we have, in addition to the Azure cloud and the mass data storage that we have, there's also a mass deployment of SQL servers. And that is something that is used by some of the projects, but not all. In fact, that didn't become available until many of these projects already got started. Drug discovery, Newcastle in the UK is using Azure to model properties of various molecules for drug discovery. And that project has been quite successful, and it's even got a commercial spin-off going. Paul Watson has been doing that. In Japan, we had somebody looking at structural analysis of predicate argument in the Japanese language. So they looked at a whole host of text, and they do a lot of machine learning based techniques. Again, on Azure, they use 10,000 cores on Azure to do this analysis. And finally, another example is this is done in the US with University of Virginia and also South Carolina, where they are looking at large-scale watershed modeling. And that project is also still ongoing and quite interesting. Now, what have we learned from this? Traditional communication-intensive MPI applications belong on supercomputers. We had a few people try to do traditional, say, quantum chemistry modeling that they were doing on a supercomputer. This is an Australian group, and do it on our cloud, and they said, this was horrible. And I said, well, I told you it would have been, but you wanted to try. Thanks for trying. So aside from that, the cloud had some really wonderful advantages. First of all, it is an environment that encourages sharing and through web access. Excuse me, I'll make it through the half hour. A lot of this is massive MapReduce data analytics on cloud resident data. That works very well. Or massive ensemble computations. You have 1,000 things that you're trying to run simultaneously, 1,000 cases. Okay? That's a typical ensemble calculation. And you can do them all in parallel. And it doesn't require lots of communication. It works very well. Also, this model of scale out as needed works well. Users prefer this. The users found that they like this pay-as-you-go model for building and rather over buying a cluster and then having to devote the life of a graduate student or two to maintaining it. Pay-as-you-go model works pretty well. In particular, you buy a cluster with, say, 1,000 cores. You want to then somehow use something with 10,000 cores. Well, your 1,000 core cluster doesn't expand, whereas the cloud can scale out if you need it to be. And this has turned out, I did a detailed survey of the users that used it, and of all the successful projects, they said, yes, we would go back and ask our funding agency for money to use the cloud rather than go out and buy specialized hardware. I see I'm almost out of time. And should I go to 1:30? Is that the time?
Yeah, a few minutes.
A few minutes, okay, I'm almost done. But what do people do here? They want to bring large-scale data analytics to more people. They want scientists to be scientists, okay? Most scientists don't want to deal with system administration. They don't want to learn to operate a supercomputer. They want to focus on their science. They use standard tools like spreadsheets and statistical packages, desktop visualization. What they would like is to be able to push a button and to have the big hard parts go off into the cloud. And they want to be able to share results with their collaborators. So what we see as a software design stack is to design a collection of data management analysis tools that's open and extensible, provides this economic sustainability model, is accessible from a desktop, encourages collaboration, and leverages this capability of these public clouds that we've got. So we're working on trying to figure out, can we build such a thing to do that? That's an interesting, let's skip this. All right. Oh yeah, so here's an example of the types of technologies. We're really interested in not basically selling you our latest piece of software, but finding out what are the tools the scientific community wants to use, and we'll put them there on the cloud. So here's an example. We have some really great support for Python, and I know that's widely used in the scientific community, as is R. And so there's this thing that has been built by a couple of groups in the Python community called Python Notebook. So this is sort of a web thing that looks kind of like a Mathematica notebook, which has got all sorts of cool things. It's a way of sort of communicating. Here's my new way of doing some computation, and here it is. It's an executable notebook. The notebook is actually running in the cloud, and it can invoke cloud resources. It can even do the back-end parallel computation. Another thing that we've worked on is something called Excel Datascope, and what it is an extension to your spreadsheet that allows you to, from your spreadsheet, you get this ribbon that you see in Excel. Well, we have a special ribbon for scientific data analysis, for importing and exporting data, doing things like outlier detection, machine learning, a variety of different algorithms. And we've released some of this open source, and we're going to be releasing more of it later. So next steps, we've been working very closely with the Internet 2 community, and we got started this notion of large-scale project with a bunch of 13 university CIOs came to us, and they said, help us. We've got this challenge now. Our people that would be, in the past, we just gave them a workstation and they were fine. Now they need data collections. They want to be able to store the data, share the data. They want to be able to mix data from different sources. And they came to us, the CIO said, what can we do? And so we had a group of us that met in March, and we started up something. We made an agreement with the Internet 2 to be a provider of cloud resource, or a broker, I should say, of cloud resource to the university communities. And so we sort of focused on two different things. One is, I should back up again, genomics research. We will do a program around genomics research. And you've heard some of the stuff from Microsoft and great interest in that here. And we'll continue that. But in terms of the long tail, workshop we've got coming up on October 15th and 16th at the University of Washington on the sort of cyber infrastructure for social science. And so there we're going to be looking at trying to find out, can we build a community that is interested in sharing data, in bringing together important data collections and the important tools that people need to study the data. And so, our goal is to try to demonstrate that we can build two sustainable collections or collections for two communities within 3 years. And at the end of the 3 years to see if we've got something now that has enough services and capability that people would be willing to see it self-sustain. So if you're interested in this, talk to me, and I'll stop there.
Thank you very much. And we have time for a couple of questions, please.
Yeah.
So Dennis, on the slide that you had about the lessons,
Yeah.
so I don't think that any of those seem particularly surprising necessarily. I was wondering, is there anything that actually struck that you didn't know ahead of time that you learned from this?
Oops. Well, I just killed that. Oh, there it is. Well, I won't go back to it. Well, in hindsight, yes, those things are not very surprising. It wasn't clear to me, though, how many users they're willing to experiment with this cloud, as long as I've given it to them. How many users would say afterwards when it's all done, saying, yeah, I would actually ask my funding agency to provide me with, instead of money to buy a cluster, provide me time on Amazon or Azure. That wasn't in the slide. It was in my more recent analysis that I've done, and that was quite strong, both in the U.S. and in Europe.
Your average astronomer, I think, is only just now coming to terms with data access through the cloud. So it's the Sloan Digital Sky Survey, things like that. And I think most astronomers really don't want to do any analysis in the cloud. The online tools, except for stuff that's very simple. To produce results for their publications, they do that on their computer with code that they've written themselves or collaborators or anything. So I like the Python notebook idea, but are there other, can you imagine other ways to bring the traditional laptop environment where astronomers are comfortable with their own codes into the cloud? Is that a possibility?
I think so. I mean, it depends upon you're talking about taking the applications that people run on their laptop, pushing them to the cloud and scale them out. Yeah, absolutely.
Applications up there rather than providing them with a fixed set of applications.
Right. No, I absolutely agree that is what you need, that capability. We have this thing that we built through the European project of this called it's called the generic worker, and it takes some application from your desktop, and through a control panel you can push it out and have one or more instances of this thing running in the cloud. Now it becomes very complicated depending upon if that application has a special user interface, graphical interface or whatever. That can be dealt with, but it's typically different for each one. But yeah, I think that's important. That's one of the reasons I'm really pleased that we are now able to run Linux VMs on the Azure cloud.
It's kind of a comment on a question, but the poster over there with Campfire on, that's what Campfire does. You go on a VM and it's like being on your own desktop and it's a cloud. So that's the idea.
Yeah.
I should go look at that later. Yes.
I mean, just as a follow-up, I think astronomers need to get over this idea that they can't use other people's tools or resources. It's black box sort of insecurity.
Yeah.
Okay, very briefly, last comment.
So, sort of following on in this last question, what about the case where you've got software that requires licenses, specifically MATLAB. And, if I'm running a big problem with, 1,000 or 10,000 cores, and don't tell me that I can do it in R or Python, okay?
You want MATLAB?
I've gone down that path, no, all right. And so the question is, well, what do I do?
Yeah, so actually, in the case of MATLAB, we've had discussions for several years now with MathWorks, and they are, I would say, warming up quite nicely to the idea of providing, this is a business decision of their part, and I think they're kind of getting it now. I don't know what will come of that. I hope it is something that happens sooner rather than later. But I'm not involved in that discussion. But you and I can talk about that.
We should talk, because I've got a problem. I could run tomorrow.
It has been a discussion. I mean, the first time we went to MathWorks about this, they said, "No way, get away from us, you devil." And then over the years, they sort of kind of figured it out. But I don't know how far along it is.
Okay. Thank you very much again. So we move to the second keynote of this session, and Mark Stalzer from Caltech will tell us about trends in scientific discovery engines.
All right, thank you. Can you hear me? Okay, super. So I'm actually going to talk about one of Dennis's slides, but in much more detail, and that's supercomputers. And so the reason that supercomputing is important for two, there's some applications that you can only do on a tightly coupled machine. All right. The other thing is that supercomputers act as kind of the Formula One race cars of the computing industry, and they drive the progress of the entire industry. So to those of you who saw parts of this talk last year, I've made changes, so I know it's after lunch, but please stay with me here. So I've already done that. And so some of the things about computing, and these have been true for quite some time, is that supercomputers are always out of commercial parts. And this was even with the Cray 1, the commercial parts they used were just very simple gates. And some of the drivers, it used to be actually the reason we had to have a semiconductor industry in the United States early was for missile guidance. And now I think it's all for virtual missile guidance, which is video games. But it's all about power and packaging. When you're going to try to get the most performance out of a computer, you have to be very careful about your power and very careful about how you package it. So this is definitely, well, we see this in the cloud computing too, but they have different constraints they're trying to optimize. And the fact is 100 megawatts is very expensive, all right? But there are devices that are extremely power efficient, like the chips that drive the iPhone or the iPad. And these computers are hard to program, but they can be easy to use if you have the right abstractions. And so this talk is kind of broken into two pieces. One will talk about the pure high-performance computing in terms of how quickly you can do linear algebra. And there's some very interesting things going on there. And then I'm going to try to make the case that we're all messed up on our storage architectures, and we need to rethink those. And the way to do this is to come up with a metric like the LinPack benchmark for storage. Okay, so trends in what I call the simulation engines, or computing without data, because they compute much faster than they can pull data in. And so the top 10 supercomputers, this is just the June one, this is this year. It's Sequoia, and it's running at 16 petaflops, which is quite remarkable. And there's another nice machine in Japan that's running at 10 petaflops, but you'll note that these machines draw nearly 10 megawatts of power when they're running. The other interesting thing is these are not accelerated. You have to go down to, oh boy, this machine is actually accelerated. And so people say that GPUs are all the future, yet the fastest computers we have right now are actually general purpose. And this is what Sequoia looks like. And you can actually play soccer in this machine room. It's big enough to do that. This is at Lawrence Livermore, if there weren't computers in it. And it's very cold. And so one of my points will be that all the parallelism, or a lot of it, is moving on to the socket. So people ask, okay, is it a processor or is it a core, anything like that? The thing to think about is that it's a socket is where a lot of the computing is happening. And so there's a socket. And of course, these things are optimized for dot products, and that's what one looks like in C++. And there's a lot of going on here, about 10 instructions. And what's interesting about this point in time is that we can compare the fastest machine in 2002 with the fastest machine in 2012. So over 10 years, they're the same architecture. So we can compare apples and apples. And so ASCII White got to 7 teraflops. This is the power architecture. It's clocked at 375 megahertz. It had 8,000 sockets, and it could complete one of these loops every clock cycle. It was finishing like 10 instructions every clock cycle. And so we'll just define that to be 1, all right? In Sequoia, it's over 2,000 times faster than ASCII White, but it's the same basic processor architecture. It's running about 4 times faster. They went up to 100,000 sockets, so there's reliability issues beyond that. And this is a tightly coupled machine with the very fast networks. But what happens at the socket level is the parallelism is now jumped to 64. And in fact, of this gain, about half of it is clock rate and just making the machine bigger and better packaging. The other half is the parallelism on the socket. Okay. And this has a lot of implications, but it's going to get much worse. So if you look at the Intel mic, it will have 50 cores on a socket, and each will be 4-way threaded, so it'll go over a few hundred threads per socket and a teraflop. And in a few years, this is going to scale out to 1,000 threads, and hopefully it'll be cache coherent. And we'll have something equivalent to ASCII White in a single socket. All right. And this is a qualitatively different programming model. You use MPI between the sockets, and now it becomes very high latency, and you have to use massive general threading within the socket. And we're going to have to rewrite our codes. We're going to have to rewrite our codes to exploit this 2-level of parallelism. So if you think of an image processing algorithm, and you had a bunch of computers, you could just throw an image against each socket, and it would, do the comparison from, tonight's observation, or what we just got from tonight, to a month ago. But you can't do that here. You can't throw hundreds of images against the socket because they just don't have the memory. So what you have to do is you have to rewrite the code so that it actually parallelizes in the image, okay, in little regions in the image. And so this is a qualitatively different model. And now we're asking our students and our postdocs and whatever to now learn 2 kinds of programming models, and it's just inevitable because the physics is driving it. And what you get is what I'm calling a socket archipelago. It's just this big sea of sockets. It can get much worse than that. We were looking in another program at exascale computing, and every one of these is another layer of parallelism. So I've only talked about 2 here, but those are the most relevant, the ones that work right in this level. So we'll get to an exascale, but it'll work for maybe 1 code. And this is a chart from Peter Kogi. And what was really interesting, some people have talked about you have to move the data and everything like that. In these supercomputers, you do not want to move the data because this is a complete trace as a part of LINPACK of one operation. one floating point operation and what it takes to stage it all up in terms of power. And it was 475 picojoules. The amount of energy it takes to do the actual floating point operation is 10 picojoules. So it's a factor of 50 just to move the data as opposed to compute on the data. So this is kind of another manifestation of what I'm saying. All right, so let's switch to data engines. And in here, progress it's very much behind what's been going on with the traditional supercomputers. They had a very well-defined, easy benchmark. Storage is actually quite a bit behind. And here you get this latency of how long it takes to access data. If it's in the register, it's 1 cycle. If it gets down to disks, it's 10 million. And remote memory, which is memory in somebody else's socket, is 10,000 cycles. And so there's a big gap. And so people have been trying to bridge this with using flash-based solid-state disks, and they've had some good success. So this is Gordon, and you can look at the architecture, but it's basically a supercomputer, but with some solid-state drive attached storage nodes, and it has what am I looking for? Okay, anyways, it has about 8 terabytes of solid-state disks. So you can actually load an 8 terabyte data set onto this machine. And it has typical supercomputing kinds of interconnects. And so this is a particular benchmark. I actually forget what this is. The nodes here is actually the size of data structure, not the size of the computer. That would be kind of big. And so you look at the performance with hard disk drives. This is very new data, came out in June. And when they ran it, so the compute's the same, but when they ran it across the hard disk array, and this is a supercomputing hard disk array, it was this amount of time. And then when they moved down to the solid state array, it was a dramatic improvement, and it's about a factor of 6.5. You also note that we're actually starting to get an Amdahl's law effect here because we're actually computing a lot more than we're hitting the disk, which is a good thing. Anyways, this is available right now on Exceed. This is the TeraGrid successor. And so there's another idea that Alex Zalzale and others came up with, Gordon Bell, was this idea of an Amdahl balance blade. So the kinds of there's 3 definitions here, and the Amdahl number is a bit of sequential I/O per second per instruction per second. And simulation codes tend to only need about 10 to the minus 5th, which means they're doing very little I/O. They're just completely computing. But they built some machines, again, using solid-state disks that were much, in fact, they used the Gray Wolf as the standard because it was a very effective data-intensive machine, and it had some good balance. But moving over to SSD, they were able to get even better Amdahl balance. And their hypothesis is that you need, for data-intensive apps, need a number of about 1 on the Amdahl number. And they're getting that with some of these machines. And they're also remarkably low power, 30 watts, and they're pretty cheap. And they built a whole cluster out of it, which is what they call Cyberbricks. And they get this whole 36-node Amdahl balance cluster in a little over 1,000 watts. Okay, so this is like a hairdryer. This is nothing, and spectacular I/O performance. And so, if you have to crunch an astronomical data set, this is a nice machine, of course, to do it on. This is going more mainstream, and Calixita, I haven't ever heard it pronounced, so I hope I pronounced it right. Working with HP on a program they called the Moonshot, and these are very tiny, And they're ARM processors, so ARM is in a lot of cell phones and things like that. And these cards are only like this big, and they can put like 200 and does it say here? No, it's over 200, close to 300 of these chips in one 4U case, and they all boot Linux. So talk about a system administration nightmare. But and each of the little virtual servers, they're building another card that has a solid-state disk, would only draw about 5 watts of power. And so you can imagine, Yahoo and Google and Microsoft cloud servers moving to technologies like this, which saves a tremendous amount in terms of operating costs. All right. How much time do I have? 5 minutes. All right. So anyways, you can go even further than this. Yes?
You said that you may expect the big data cloud to move to this technology.
It could.
But do you see any showstoppers for that, or is that actually going to happen?
You would have to ask the people that run it, but it seems that given that they're basically running a bunch of commodity servers, these servers are going to keep shrinking too, and their workloads are designed to handle these, work well on those kinds of things, and so I would imagine it would.
But cost-wise, are they competitive?
The power is much lower. So I'm running out of time here. And I want to get to the 2 punchlines on the whole thing. So the one thing, we can do a lot better, though, for data-intensive applications. In fact, we can do 100 times better than what we're doing now with existing technology. And that is by using parts that people, that the companies like Apple and are putting into things like iPads. And what you can do is you can array these parts up, and you can, on a single blade, all right, you can get like 64 of them. They're small. They're cell phone parts. But when you aggregate it all up, you get about 6, with flash on a blade, you get about 6 terabytes. But in terms of the performance, in terms of bandwidth and latency, it's about 100 times faster. And then you can get up to about a 4 teraflops accelerator. So again, this is very Amdahl balanced. And it also fits on a single blade. It would look something like this. It just got published. And it has huge implications for data to discovery, because it can read its entire data set 100 times faster just because it has so many I/O channels and it doesn't have software stacks on the I/O channels. It's 100 times faster in random access. It's Amdahl balanced. And so this is qualitatively new because it's a factor of 2, factor 2 orders of magnitude. You need to have the number of reads much greater than the number of writes. This is for a very technical reason. But you can imagine one rack of these things, about ½ petabyte, handling all of the LSST processing, okay? And it'd be good for this as well. And in fact, I looked at one server, and one server on 1 billion web pages could store 1 billion web pages and handle Google's basic search workload. Now, they do a lot more, but this factor of 100's big. Its performance on triple stores, and again, I'm going to run out of time because I want to get to something else, is probably, we think, about 100,000 times quicker. And maybe this is starting to look at what a storage metric would be, because this is unstructured, semantic data. And maybe these are the kinds of metrics we should be looking at, things like triple store performance, to get the data field to where the simulation people are at. So this is the fun part of the talk. So there's some speculation it only takes 10 to the 16th ops that the human mind only does 10 to the 16th ops. And the whole point of these next 2 slides is to show how far we have to go in our trends in computing for both storage and computational ability. So I'm just stipulating this. You don't have to believe it. And it's not my number, so it's not my fault if it's wrong. All right? So we could build these now. Okay, Sequoia is already running faster than this, and you could build FlashBlade-like engines this fast too, probably at about 2 megawatts. Okay, that's the important point, 2 megawatts. Oh, for all of you people who write simulation codes, an engine like this would checkpoint in 10 seconds, which is just extraordinary. But now there's another big data engine, all right? This is actually a monkey brain, but and so we, by definition, we're at 10 to the 16th. The memory actually in a storage-intensive system, as I've described, would be actually quite a bit larger. And so this would only be about 10%, and it forgets all the time. The bandwidth is roughly the same. It just depends on where you are in the hierarchy. But the packaging is rather remarkable in that it's really small, and you saw how big Sequoia was in terms of the number of cubic feet of space, and it's a factor of 8,000. All right, so these numbers are kind of like plausible. Here's the amazing number. This thing only draws 25 watts, all right? So it's 80,000 times more efficient than our current technologies, even if we do every trick we can with our current technologies. So in terms of trends, we got a long ways to climb, all right? And then if somebody knows the algorithm at Microsoft Research here or something, please let us know. So, all right, back to the socket archipelago, and I'm almost done. So again, let's look at where the parallelism is at. So at the cluster level, I don't think we can really go beyond 100,000 sockets for reliability issues and size issues and things like that. And the latency between the sockets is about 1,000 watt. In a socket, we might go up to about 10,000 threads. This is just in 5 years. And so what we have is a latency difference of 1,000. So this goes back to this whole idea of MPI is basically working between all the islands, okay? And this is where the archipelago idea comes from. And then the threads are, the tribes on the islands, okay? And so they can communicate much, much faster here than, rowing a boat over to the next island. So we're going to have to restructure our codes. And there has to be very large caches on the sockets, because the second you go off socket, that's it. All right, you have tremendous latency. And I'll claim that the non-volatile storage, whatever technology it is going to have to be stacked on top of the structures as well. Otherwise, they're out. They take forever to get to. I don't have time for this. How much time do I have? I'm okay. So anyways, you can look at the slides later. There's some ideas on programming these things. But my concluding remarks, last slide, we're not stuck with clusters. Off-the-shelf technology is not what you just get at Fry's, but the things that we know how to do and we can quickly build. What is a top 500-like benchmark for data? Because this will drive the development of the systems, okay? It's been fantastically successful for dot product engines. We want something similar for data engines. Get used to threaded programming, or find somebody who can write a library to abstract away what you're doing. And also think of what can be done in terms of a shrinking 10 to the 16th ops system, because that's where the technology is ultimately going, and that's it.
Thank you very much. We have time for a few questions. Yes, Matthew?
I have two questions or two comments. Firstly, on the benchmark for data, a result that I'll show on Wednesday is some experiments I've been running comparing triple stores against relational databases, retrieving unstructured data.
Okay.
It turns out that the triple stores are faster than relational databases.
I believe that.
In just off-the-shelf components. On the programming side, so this would mean advocating both MPI parallelism and GPU type parallelism coding as the sort of thing we should be teaching.
Right.
Is essentially what you're saying.
Actually, MPI, yes, but I would say programming with general threads. GPUs are very SIMD machines. And
GPU is a bracket term for that sort of threaded,
we have to teach threaded programming.
So this is lightweight memory usage, but small computational algorithm step type.
Exactly. And how to synchronize them, and how to, what 10,000 are flying around at once. Yeah. Dan,
please.
Just so you were talking about needing to have reads much larger than writes.
Yes.
And then you followed it up by talking about checkpointing.
Yes.
Which is exactly the opposite.
No. So the problem is that flash memories are programmed by tunneling through their oxide, right? And eventually you break it down. And so there's some technical things in that it looks like for a given flash part, if you relax non-volatility constraints to like a week instead of 10 years, you can get well over 1 million writes. And so the point is that a machine like I was describing would have to be like go to sleep for every few days so that you could swap out flash parts. So if a programmer tries to use it as just a read-write system, they're gonna burn it out, and you should charge them for that. So you want to just think in terms of reading the data a lot, not only writing it. But a checkpoint every hour is no big deal.
Even though you're never reading those checkpoints.
Right. Exactly. Correct. Right.
By the way, you can also repair the outside layer.
Yeah.
You heat it up, it repairs itself. So you just have to cook it every night.
Oh, okay. So it has to go to sleep.
Yes, final question.
The 10 to the 16 ops 25 watts machine is a nice piece of technology, but you cannot trust it. So I wouldn't go that way.
No, it just needs the 3 laws, right?
You can't do it with CMOS, okay? But graphene-based structures will get down there, and they're actually, I'm not a device physicist, but they're actually even more reliable than CMOS parts. But you still can't trust it, I agree.
Okay, thank you very much again. And we'll move to the panel discussion. So please, the speakers for the panel discussion.
So we need to, in order to get to sort of exascale and exabytes of data, we need to get on a completely different curve. So I think Mark gave a really wonderful start to this. But what we'll see is that most likely we will build systems with millions of components, so with very high density, low power. And then there would be also all sorts of interesting issues coming from the programming, the change in the programming paradigm, not just about the multiple, how do we handle the threading, but also how do we handle the frequent failure of the components. And how do we write codes which are also self-healing or recover from errors? And how do we create toolkits where we can basically simulate hardware failures randomly at will into the different pieces of the code so that we can actually see how they debug the code, essentially recovering from all the errors. And on the power side, if we are, for example, focusing entirely on the data-intensive part. So, for example, if we want to build a very heavy-duty AMDAL engine that really streams data at AMDAL number of 1, we might consider, for example, cache to be an impediment. So today, a lot of the power, so when Intel builds processors, they make all sorts of trade-offs between how much silicon and power do they devote in the chip to the floating point units, to the I/O devices, and also how much real estate is spent on cache. And when basically cache makes a lot of sense when we do numerical computing, when data locality gives us a lot of advantages. When we want to stream a petabyte of data from the disk through the storage hierarchy onto the CPU, essentially the cache is giving us very little. So in a sense, if we could build a special processor, stream processors basically, this is to some extent why the GPUs are so good in doing what they do, because they have almost no silicon wasted on the I/O, or and basically they also have a very efficient streaming through so we can build basically all these pipelines. So just to get started.
Okay, I'll say just a few words. So a topic that I think is worthy of consideration is what will the computer systems that the community needs to build or acquire or pay for look like in the future. We've heard that they need to be able to accumulate very large amounts of data, perform analysis on that data. Presumably, we haven't heard so much about this, but also integrate simulation with data analysis for various reasons. So how many of those systems should we have? Will we be able to perform all of our computation on systems operated by the likes of Microsoft, or will I don't think it necessarily makes sense for every university to acquire such a system. Will national centers acquire them, and if so, will they look like our supercomputers today? I think they probably won't. So those are some questions that perhaps people have opinions on.
Well, the advantage of just speaking is that you know what I think. I think, again, power is a crucial issue. Workforce development is very important for all sorts of things, from threaded programming all the way up to how to use data analysis tools, and those are. And also finding, like I said, what's the metric to drive data-intensive systems, because we could do a lot better than we're doing. And flash technologies are actually relatively primitive. There's other emerging technologies that could do a lot better.
Any questions, comments?
So, all of you made essentially an important point that we've been leveraging for scientific computing commercial developments driven by something else, say GPUs or cell phone technology and so on. I'm thinking that likely we're going to see a lot more 3D video coming, both real and simulated, and that might produce next generation of GPU equivalents, if you will, or video card equivalents. Is anybody thinking what might be the architecture of those and how can those be turned into scientific computing engines? Or speculate, how would you do it?
Already, I think the current generation of GPUs can render more than the data that we can feed it. So they are already, so in a sense, there is some race going on, but essentially the bottleneck is already how do we get the data and the word model into the GPUs, basically. So already a tablet can render a very complex game. And so I think the trick will be rather that, okay, so how do we get, for example, in terms of visualization, how do we get the data again to the engine? How do we, maybe we will be trading more and more CPU because CPU will be essentially quote unquote free. So using much fancier compression techniques, basically trade more CPU against bandwidth. That I think that might happen. So we come up with extremely clever compression algorithms. So.
My guess is that they'll look a lot like better versions of our current GPUs, and the trouble is that these things are difficult to program, and so that's why there's a shift back to a model that is actually, in some sense, more energy inefficient, but they can get more performance out of it. But if you really want to just build a holodeck, the final drivers are probably going to be, GPU-like structures, like what we have now.
About power consumption, you said CPUs are essentially free, but I'll talk to you about our ASCAP telescope we're building. One of our biggest problems there is that we've got this machine sitting in the desert, which requires 10 megawatts, and that's actually dominating our running costs. If CPUs are free, but their energy won't be, so do you, I know the power requirements are slowly coming down, but do you see any big leaps in the future, and that's otherwise the CPUs won't be free.
So, well, Andrew Chen, who was the head of Intel Research, now is at Chicago, he has a wonderful talk about this, so the 10 by 10. So that so basically the current generation of Intel CPUs is like a Swiss Army knife 1,000 times over. So it has an instruction set that is way, way too complex, and basically any coprocessor, so an FPGA or a signal processor chip or a codec hardware chip, so basically a DSP chip, each of them can do 100 times better in a very specific task at the same power budget. Okay, so why not build an array of those, a mosaic of those on the same silicon where we turn all the different components on and off at will instead of trying to execute everything in a general purpose hardware. I think that's a very good perspective. Of course, it goes kind of orthogonal to Intel's worldview, so no wonder that he left. So.
And there's a lot of people have a lot of ideas for reducing power, running at much lower power and accepting higher error rates. I think it's not clear which of those will work out, given the challenging economics of scaling any of these up to mass production.
So you said that we needed a different sort of way of teaching people how to program. And at the eScience meeting in the one in North Carolina, Michael Less made an interesting comment that surprised me, but all the computer scientists in the room kind of nodded their heads. And he said that the improvements with all the Moore's law parallelism, that we forget what he was claiming about improvements in software. And he said that we're better off using 1980s hardware with today's codes than the reverse. So the question is, in order to take advantage of this, what are the sort of software problems that need to be solved in order to really take advantage of these kinds of hardware improvements? Like I have some problems that are not solved by Moore's law and parallelism, but eventually, I think, solved by some clever person figuring out how to do it better. But so what should we start to be teaching ourselves and our students?
Well, an n log n algorithm beats an n squared algorithm any day, and so it's important for people to study, the best known algorithms, and there's numerous examples of this. Okay, the point is, my point I was making is, if you want to exploit the capabilities of the chip, you have massive data sets, or you're trying to model global climate change or something like that, then the students need to, in addition to knowing algorithms, need to know more about parallel programming, thread-based programming. The computer science departments know all of this, and they know how to teach it, but I mean, it's not common for scientists to actually take these computer science courses. So it's there. It's just another aspect of education that needs to. It's one more thing for the students to do. So
it's well known, but only to those who know it well. Is that?
I'd like to comment on. Can I make a comment there? So, right. So the advances that Michael was talking about were algorithms, not software, which are different things, of course. But so I'm not sure that many computer science departments teach parallel programming classes.
We do.
Some do, but not, I think it's not quite as common as you might think. But so I wanted to observe that, as I understand, at a place like Google, I'm not so familiar with Microsoft, there are thousands of people writing very large-scale parallel programs, but they don't know about multi-threading or MPI. They do it using libraries that have been developed that meet the particular needs of their applications. And I think you mentioned the importance of libraries in your talk, but in a sense, if your students are writing multi-threaded code, you've failed in some, well, not the professor, but the community has failed in some way to build the right infrastructure.
I mean, an example to that is OpenGL, and it renders all these beautiful images, and it can be highly parallel on GPUs, but the people who use it don't have to know the parallel programming.
Is that a question of algorithms or language? So if we recoded the word in Erlang, we would suddenly get all this for free.
Well, I mean, one wants efficient. Algorithms and language are different. So certainly writing multi-threaded code using a pthEdge library is not a recipe for happiness, and using Erlang is probably far more effective. But it doesn't. Erlang in itself doesn't make your algorithms n log n instead of n squared. Right?
No, but if you end up with people having a better natural understanding of how multi-threaded things work, then they will intuitively make up their own more naturally threaded algorithms.
George? Something different. You and also Dennis have been talking essentially about supercomputer equivalents for data-driven things, whether it's machines like Greywolf, whether it's the giant data centers, and they're optimized for essentially for web search. Right? And there is the cloud, which is a few of the centers. But don't you think that what we should be going to is a whole hierarchy from cloudlets, clouds, the whole dang climate, and the architectures that need to be optimized for different things, like certain types of data mining, and by architecture I mean not just the data center itself, but down to the blades or maybe down to the processor level, instead of one catch-all thing.
You're still going to have some basic things that you can assemble the machines out of. I mean, that's my only.
But I'd like to throw in another thing. So I was in Delft this summer at a data-intensive workshop related to the grid forum. And there was an eye-opening workshop, so where there was a lot of discussion, essentially, the file systems. And so people are obsessed with POSIX file systems and scaling them to petabytes and so on. And when you think about it, so basically in the underlying file system, we have a very complex set of hierarchies where we know exactly where every piece of data is located at different granularities. And then we hide everything, and POSIX is basically a simple data stream. And then after that, we build yet another set of tier of data structures to again rebuild to figure out where the data is actually located on the physical storage. It just really doesn't make sense when we get to very large amounts of data. And so there's this recent trend of exposing a lot of these details in the file systems, including the new version of Windows. So there is a lot of object level access basically to data items. But this was really, it also started to kind of realize that what is Hadoop and MapReduce in this world. So basically it's an ultra simple scheduler, that very, very dumb I/O scheduler. It's people have spent 20, 30 years to write schedulers which work on supercomputers and schedule basically CPU computations, but it is not very easy to co-schedule basically different types of I/O operations, random access versus sequential. They mess up each other and interact. And when you have only sequential scans on the Hadoop-like systems and only a single linear crawl of the whole data, it's very simple to deal with, easy to predict the behavior. And basically, at the same time, in database systems, people have spent 30, 40 years, again, optimizing the complex I/O happening inside the database engine. And so in this world, I think there is a convergence kind of, I think, slowly emerging that somewhere there will be some file system which will merge the best properties of both the traditional file systems and basically the database localities and object granularities. So.
But it seems to me that we sort of these, as you put it, the web searching optimized systems where it assume that data sits in one place and then computation is performed on it. But I mean, inevitably it seems there are some storage devices that are cheap but slow and some that are fast but expensive. And so data is going to have to move between these different sorts of systems. So you may well have heterogeneous systems that are optimized for different
And your
purposes.
applications could even be aware of those things.
Right.
So.
Any more questions or comments?
Again, something different. So moving data is where most of the trouble is, right? Power or money or time. And so is it worth thinking in terms of changing our algorithms to essentially be data mining streams in real time and never see the same data again, which will be a very different approach from having stationary archive and poking at it from all different directions?
It's happening, isn't it?
Well, at some level.
LHC.
Well, but all of that is throwing away data on instrument level. What I'm thinking is at science grade level.
It may get to the point where it's actually cheaper to recompute things than to pay the cost of moving the data.
Well, for simulations, but for the real life measurements, once you
of course,
it's gone, right?
I think good data can outlast a lot of bad computation.
It does often, right?
You're not able to afford to analyze the data again and again.
Yeah.
They can only do it once.
Yeah, we're going to do both. I mean, you're already doing both. I mean, you take the data stream, you extract something from it in a pipeline style, and you put it away in case somebody else has a clever idea later.
Yes. Well, what I'm worried about that we may not be able to afford that second step with the exponential growth as we see it.
Well, I mean, George, you sort of know this. We're already at that stage. For some, not so much yet for astronomy, but earth science and to some extent planetary science.
We're there in astronomy now.
We're there in astronomy.
Yeah.
So I was thinking certainly by the time of, say, ASCAP, we could be at that stage.
That's right.
Well, LOFAR is already generating more data than LSST.
Yeah, but that's...
But I would argue even with a lot of the embodied simulations that we run on our supercomputer, we are already there because we store many fewer snapshots than what would be ideal for our science.
Right. And for climate models too.
So with ASCAP, it will take about 12 hours to read 12 hours of observed data off the disk. So you never ever want to do that.
Right.
So, and it's arguably cheaper to observe it than read it off the disk. So in which case you don't store it, obviously. And so we're planning in ASCAP to do all that source extraction, everything on the fly. If one day you do get this better algorithm, you're going to need a hell of a computer. This disk actually is the problem. You need these fantastic disks to redo it.
3 minutes. Oh, I have a perfect question for 3 minutes. Anybody dares to speculate about quantum computing?
That sounds like Warwick's.
Maybe yes, maybe no.
Can I on the question? You've been given some really good remarks of what can be done with commercial and inexpensive hardware. Any comments on disruptive technologies like quantum computing or optical computing?
I would say memory stores. They are actually be much closer to reality than I think quantum computing will be in our lifetimes or in my lifetime. Memory stores will rewrite computer science if they work, if they become practical, because every memory element will be also able to do arithmetic operations. So all of the algorithms we can throw out in that world. So it will be an interesting world if that comes to.
Okay, thank you very much, and let's clap for the.